Welcome to question 3 of the 2017 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. So for question 3 we have f with a domain of -3 to 0, have the rule f of x equal x plus 2 all squared times x minus 1, and we want to show that x plus 2 all squared times by x minus 1 expands to give x cubed plus 3x squared minus 4. So to start with, we're going to expand x plus 2 all squared. So therefore, we have x plus 2 all squared multiplied by x subtract 1 is going to equal, and now this is a binomial expansion, so we'll get x squared plus 4x plus 4, and then that's still going to multiply x subtract 1. And now, just so we don't make any errors when expanding this next part, we're going to set up a grid, and the three terms across the top are going to be x squared plus 4x plus 4, and then we're going to have x subtract 1, which is what the green is multiplying by. So x times x gives x cubed, and then 4x times x gives 4x squared, and then 4 times x gives 4x. X squared times -1 gives -x squared, 4x times -1 gives -4x, and 4 times -1 gives -4. So they are the 6 terms that we get out of that expansion. So just rewriting them out here, we'll get x cubed plus 4x squared plus 4x minus x squared minus 4x minus 4. And then we can see the positive 4x and the negative 4x would cancel. And we also have negative x squared as being a like term to 4x squared, so that would combine to give 3x squared in the next line. So that means that this is equal to x cubed plus 3x squared minus 4. And that is what we were being asked to show at the start of the question up here. So from the examiner's report, we can see that almost 80% of students got that correct, and that the question was answered well. Although some students either did not fully expand the cubic or made notational errors by omitting the brackets on the quadratic. It should be noted that x squared plus 4x plus 4 then times by x minus 1 with no brackets is not equivalent to the expanded form that needed to be found. So for this to be correct, we needed to have brackets here and here around the quadratic expression. For part B, we want to sketch the graph of f on the axes below, and we need to label the axis intercepts and any stationary points with their coordinates. So importantly, f has a restricted domain of -3 to 0, so we need to keep that in mind when we're sketching this graph. And now, before we go too much further, based on the answer from part A of this question, we know that f of x, which did have the factorised form over here, can be expanded to x cubed plus 3x squared minus 4. And it's going to be helpful to have it in expanded form when we get to finding the stationary points of the graph. So for starters, if we find the y-intercept of the graph, that occurs when x equals 0. And you can use either form of the equation to do that, but f of 0, if we do it for the expanded form, will just give 0 plus 3 times 0, which is just 0, so we get subtract 4 is the only term remaining. So the y-intercept is going to be down here at 0, -4, and it's also an end point of the graph because we cut it off at 0, and the square bracket means that's going to be a coloured in dot. And then we can consider the x-intercepts of the graph, which is when y equals 0, and the best form to have the equation in when we're solving this equation is the factorised form. So we're going to have x plus 2 all squared times x subtract 1 squared equals 0. And now, using the null factor law, we have x plus 2 could equal 0, or x minus 1 could equal 0. And solving those equations, we get x equals -2 or x equals 1. But based on the domain that we're sketching it over, the only one we're interested in is x equals -2. So there's going to be a point up here where there's an x-intercept. And now, just before we go on to finding the stationary points, we're just going to consider the other end point of the graph. and that's when x is equal to -3. So when we do that, we have f of -3, so we'd have -3 plus 2 all squared, multiplied by -3 subtract 1, and that's going to equal -1 squared is +1 times -4, which is just going to equal -4. So that means at -3 the y value is -4, and because of the square bracket up here, it is going to be a coloured in dot. And now the last thing we need to consider are the stationary points, and they occur when f dashed of x is equal to 0. So we have f of x in expanded form here, so therefore f dashed of x we can easily find by taking the power out the front and subtracting 1 off the power, so we get 3x squared plus 6x plus 0 for that last term. So therefore the equation we're solving is 3x squared plus 6x is equal to 0, and that's a quadratic that we need to solve, so we're going to factorise and use the null factor law. So factorising out a highest common factor of 3x, we'll leave behind x plus 2, and that's going to equal 0. So therefore, according to the null factor law, x could equal 0 or x could equal -2 are both stationary points. So now we well and truly have enough information to finish off this question. So our graph's going to look something like this, with the turning point at -2 and another stationary point at the y-intercept and endpoint. And technically speaking, the graph you can check goes through the point -1, -2. So for accuracy, our graph needed to go somewhere close to that point on the grid. So just before we finish up, we're going to put coordinates on all of these key features. So this is -3, -4. This is -2, 0. And this is 0, -4. So they were all of the key features that we were asked to give. So from the examiner's report, we can see that 36% of students got full marks for this question. The examiner goes on to say that there were some very good graphs that were drawn by students. Common errors included using R as the domain rather than the restricted domain that was given, and graphs that looked more like an inverted parabola than a cubic, due to the lack of recognition of a stationary point located at the same value as the y-intercept, which we discovered on the previous slide.